Okay, we're recording. I wanted to start by doing a couple more problems having to do with the relative velocities that we did some of yesterday. And these are the Lorentz transformations that we were using yesterday, and most specifically, we're using these velocity transforms. But I think on one of the problems, we're also going to use coordinate transforms too. So we'll see how that goes. And by the way, these Lorentz transformation equations are on the formula sheet. Lorentz coordinate transforms and then Lorentz velocity transforms. So just be a bit careful with them as far as signs go, and you should be okay. Okay, the first one here, this is relatively straightforward thing. Space pirates have stolen a geosynchronous satellite used for broadcasting reruns of Gilligan's Island. The president is outraged, sends the Marines after the pirates in our fastest spaceship. And the pirate ship, according to Earth observers, is heading out of the solar system at 0.80 C, while the Marines are following them at 0.95 C, also according to Earth observers. So for observers on the Marine ship, how fast will they appear to be gaining on the pirates? All right, I'm going to do a quick sketch here to try to figure out or sketch out what might be the S coordinate system and the S prime coordinate system for this situation. And just going to have Earth here. This will be the S coordinate system. And then we'll have a marine ship that's gaining on the pirates. And I'm going to have this be the S prime system. So we want to know the speed of the pirates relative to the Marines. And so this is going to be the S prime coordinate system. And the S prime coordinate system is moving in that direction at 0.95 C. So 0.95 times the speed of light. And that would be, well, that's the U that shows up in these things. It's the speed of one of the coordinate systems with respect to the other. The pirates are going to have a velocity V, I'll call it V sub P, I guess, and that's the velocity with respect to the Earth. So that's 0.9 or 0.80 C. And we want to know what is V sub P prime. And so this is like the V sub X prime that we have here. I just put a P on it because it's for the pirate ship. But V sub X prime, or the velocity of the pirates in the primed coordinate system, would equal the velocity of the pirates in the Earth coordinate system minus the relative speed between the two. And then we divide that by 1 minus U V sub P over C squared. And the numerator up here, I'd have 0.80 C minus 0.95 C. I'd get minus 0.15 C for the numerator. And that makes sense. That's the non-relativistic speed. And if we were just doing this like people walking down a street or on moving sidewalks or things, you'd say that if somebody was walking faster and somebody was walking slower, the difference between their speeds would represent the relative speed. But again, for relativity, it doesn't quite work out that way, or when the speeds are close to the speed of light like these are. So we'll have to have 1 minus, we'll have U, which is 0.95 C, times V sub P, which is 0.80 C, and then we divide by C squared. So the C's all divide out. So our V sub P prime in this case is going to be minus 0.15 C divided by 1 minus 0.95 times 0.80, whatever that happens to be. One minus 0.76 is what it happens to be, which is 0.24, I think. Anyway, I get minus 0.6, well, let's see, rounding to two significant figures, minus 0.63 C. So actually, it looks to the Marines like they're gaining on that thing a whole lot faster, but from our viewpoint, they're gaining on them at 0.15 C, or an Earth viewpoint. But it's different for them. Time and speeds end up being different. Time and space end up being different. So there's another one. Oh, I did the whole thing on here. Okay, that's all right. We'll have that worked out. Here's one that I used to use a homework system called Sapling, where there'd be online homework, and I found out that there was absolutely no correlation between student scores on Sapling and their performance on tests that I gave them. And so, and other teachers have noticed the same thing for the online homework systems, that it's too easy to find the worked out solutions to the problems. And so you can have people that just figure, oh, I'll just turn in perfect solutions and I'll know everything I need to know for the test. But it's the process of figuring out how to make the solutions that helps you solve the tests. So that's something that you have to be careful of. Anyway, here's the problem. It's kind of wordy. It's when a high energy photon passes near a heavy nucleus, a process known as pair production can occur. As a result, an electron and a positron, which is the electron's antiparticle, you knew that, I think, are produced. In one such occurrence, a researcher notes that the electron and positron fly off in opposite directions after being produced. Okay, that's the usual thing, each traveling at a speed of 0.589 C. The researcher records the time that it takes for the electron to travel from one position to another with his detector as 28.5 nanoseconds. How much time would it take for the electron to move between the same two positions as measured by an observer moving along with the positron? Okay, well, something we're going to have to figure out in here is the velocity of the electron with respect to the positron. And what we have is the electron going in this direction, and I'll just put a little minus sign here. This is 0.589 C. And the positron is going in the other direction, and I'll just put a little positive sign here at 0.589 C. And then we've got the laboratory guy who's just standing here watching both of them. Well, having some sort of instruments that manage to do that, but we can figure out the relative velocity of the electron with respect to the positron. And let's see, if we let the laboratory frame be S and the positron be S prime, then we can try to figure this out here and see what it's going to look like. We will want to know v sub x prime, which will be the velocity of this with respect to the other thing. Now, one thing that's going to be weird in this situation is we've got the positron moving to the left, the S prime reference system. So the equations we've got, we're going to have to change the sign on U. So here's the expression we've got for the relative velocities when U, the S prime system, is moving to in the positive X direction. We've got it going in the negative X direction. So our V sub X prime, this is going to be V sub X here, and this is going to be U. V sub X prime is going to be V sub X plus U in this case. And then on the bottom, I'll have 1 plus U V sub X over C squared. So you have to remember how this equation happened to have been defined. And it helps if you can kind of draw an S and an S prime system for the original situation. But that's what we'll have. And then see if the numerator checks out to what you would get if you didn't use special relativity. And U is 0.589 C. So I guess, yeah, that'll work out. And U plus V sub X would just end up being, well, it'd actually be more than the speed of light. And that's what we would predict if we didn't have special relativity. But it's not going to be more than the speed of light, and that's why we've got this going on here. So our V sub X prime for this situation, the speed of the electron with respect to the positron, 0.589 plus 0.589. I don't feel like doing that in my head today. Is 1.178, and actually we would keep that many significant figures. What we have there, and then we'll have 1 plus 0.589 C times 0.589 C. I guess I can just square it then, divided by C squared. And V sub X prime, the velocity of the electron with respect to the positron, will be the 1.178 divided by 1 plus 0.589 squared. And it ends up being 0.87. I think I can keep 4 significant figures on here because of the way they're going to add together. 8746 C. So now that's something I'm going to need later, but that's okay. All right, use time dilation to first figure out the time that passes in the proper time frame of the electron. Okay, well, the laboratory sees the electron as moving, and so the time interval that's recorded in the laboratory is actually T prime. It's not the proper time. The time in the frame of the electron is the proper time. And so let's see, we will have T prime is equal to gamma times T. This will be the T for the electron. And so T is going to equal T prime divided by gamma. And the T prime was 0.589 C. So no, it wasn't. Where was it? Oh, it's 28.5 nanoseconds. Okay. So and dividing by gamma, didn't figure out gamma yet. Um, I'll just do it up here. Okay. And beta is 0.589, so I'm using the 1 minus beta squared version of gamma. So and I get 1.23. And I may as well, actually, it'd be 1.24 with three significant figures. So this will give me the time and the, oh shoot, why did I put in multiplication instead of division? I don't know, because they're one button away from each other. I get 2.2 or 22 point, actually 23.0 nanoseconds for the time that would pass for the positron. Now, let's see. That's the time that passes in the proper time frame of the electron. Calculate what the time interval would be in the frame of the positron. Okay, well, the positron is going to have an electron moving with respect to it at that speed, and they would say moving clock runs slow. So we're going to have a new gamma for the positron viewpoint. We'll have gamma is, this is going to be, I don't know what to call it. I'm just calling it gamma. So 1 over the square root of 1 minus 0.8746 C. Actually, if that's beta, I just square that. So and I get a gamma value of 2.066. Let's see, 3. I can keep 4 sig figs on this. So that's a pretty good big gamma value. Now, we're going to have a new T prime here. We've got a time interval in the electron reference frame of 23.0 nanoseconds, but in the positrons, from the positron's viewpoint, we will get a T prime is going to equal gamma T. This is a proper time. So we'll have 2.063 times 23.0 nanoseconds. And it's going to be even longer than what was recorded in the laboratory. Okay, 47 point, I think we can keep four, no, just three significant figures here. So 47.4 nanoseconds is what will be observed in the reference frame of the positron. All right, that's one way of doing it. the other way that they recommended trying is to use the Lorentz transforms to examine the two events that take place in the researcher's reference frame. When the electron leaves the origin and when the electron passes a point in the detector 28.5 nanoseconds later. So let the researcher's reference frame be the unprimed frame, okay, and the positron's frame to be the primed frame, which is moving in the negative direction with a speed of u equals minus 0.589 c. So okay, something we are going to have to figure out is the second event. The first event is pretty simple. First event happens at t is equal to 0 and at x equals 0. That's when the electron leaves the origin, and we can just define that to be time 0. The second event, and this is from the researcher's viewpoint, is going to be happens at t equals 28.5 nanoseconds. And hopefully we can get away with using nanoseconds throughout and not have to convert the time on there. We'll see. But it's going to happen where that thing which is moving at 0.589 c in the laboratory reference frame, how far has it traveled in 28.5 nanoseconds? So x is going to equal, let's see, well, we'll have just 28.5 times 10 to the minus 9th seconds times, didn't leave myself enough room, the fraction of the speed of light that it's going, 0.589 c, times 3.00 times 10 to the 8th meters per second. And so this x value is going to end up being, let's see, okay, x is going to be 5 point, well, how many sig fig? We can only keep 3 sig figs. So 5.04 meters. So that's the second event. First event happens at the origin at time 0. Second event happens 5.04 meters away at time 28.5 nanoseconds. And we're going to figure out, what are we figuring out? That, let's see. I forgot what we were doing on this problem. Oh, how much time between these events? This thing said it was 47.4 nanoseconds. We would like to know what the time is for this second event here. So let's just plug in and see. We do have to use a positive value or a negative value for u. And so they have you do this instead, which is okay. Anyway, t prime is going to equal the gamma, let's see. This is the gamma value for going from the laboratory frame to the primed frame. And so it's the one we figured out in the first part of when we had 0.589 as the relative speed. It's 1.23, or was it, 1.24. So gamma is 1.24. We could have just figured it out again. The time of that second event is 28.5 nanoseconds. And I may have to write that as 10 to the minus ninth seconds, I think. Okay, and then it would be minus, but I'm going to have a negative u here of 0.589 times the speed of light. And then our x position is 5.04 meters. Oh, this is negative here. So almost forgot that. And then I'll be dividing by c squared. But there's a c here, and so I'll be dividing by just c, which is 3.00 times 10 to the 8th meters per second. Yeah, then I'll have seconds on here, which I can probably figure out in nanoseconds if I'm smart. Okay, now a minus and a minus is going to make that a plus. So I'll have 1.24 times 28.5 equals 9, or minus 9. And then I'm just going to put the plus in. 0.589 times 5.04. Oh man, and I hope this comes out right. I get, with what I've done here, I get a t prime of, let's see, 47 or 4.76 times 10 to the minus 8th, which would actually be 47.6 times 10 to the minus 9th seconds, which is 47.6 nanometers. Now, it differs from the value I got before. I had 47.4, nanoseconds, not nanometers. I had 47.4, and I think the difference is round off error. Throughout this one, I only had 3 significant figures, and on the other one, for some of this stuff, I was able to use 4 significant figures. So that's probably why there's a difference, but or that is why there's a difference. But you can do some of these problems 2 different ways. So the one way was just, well, I did have to use the relative velocity equation to figure out part of this, but then I was able to do it just with time dilation. And this way I was using the Lorentz transformations. By the way, I read this morning, I was wondering about Lorentz's first name, and for some reason I thought it was A.E. Lorentz, but that was somebody else, I guess. Anyway, I read about Hendrik Lorentz, who's the guy who worked these out, and he actually did it in the, I think in the 1880s, and physicists had realized that when Maxwell came up with his equations in the mid 1800s, that built into them was the speed of light. And they were trying, at the time, they thought that light must travel through a medium, and the medium that they thought it traveled through, they just gave a name to it. They called it the ether, or sometimes the luminiferous ether. They referred to it as that. Try saying that 5 times fast. It doesn't work very well. But anyway, they thought it traveled through the ether, and Lorentz worked out these equations to try and figure out how the speed of light could be the same for observers in different reference frames when you had this ether that the light traveled through. So these transformations were developed. Einstein comes along, and I think he developed the Lorentz transformations independently. Apparently, he didn't know about the work of Lorentz. And Einstein just threw out the idea of the ether. He said, light travels in a vacuum. And it carries its medium with it, which is the electromagnetic field. And so, but we still call them the Lorentz transformations because Lorentz was the one who did it first. But anyway, there we have a kind of a complicated problem. Okay, the next thing I want to do has to do with, let's see, the Doppler effect for electromagnetic waves. And start another blank sheet of paper here somehow. I discovered part of my problem with having equations vanishing was because I've been using Office Libre, and for most Word documents that you open, it deals with them just fine. But with some of the equations that I put in previous years into Word documents, I was using software that Office Libre doesn't recognize, and so my equations would go haywire. So that was part of the problem, and I realize that now, so I hope I can not have problems with it going forward. Although if I just last through the next week and a half, I should be okay. But the relativistic Doppler shift did show up in our study of sound for light, but I don't think we did anything with it when we were studying that. But here's what it works out. And this is a source approaching an observer. Approaching observer. And the frequency shift that's observed ends up being this: C plus U over C minus U, and U would be the speed at which the source is approaching the observer, and this would be times the initial frequency. Now, we will probably be more interested in the wavelength, and we can get it if we just recognize that the frequency is equal to C divided by the wavelength. And so C over lambda would equal the square root of C plus U over C minus U times lambda naught. Lambda naught, you figure that the thing that's giving off the light is the light leaves it at its laboratory or its proper wavelength or its proper frequency, and then it's observed at something else. Well, we've actually got, whoops, this is supposed to be C over lambda naught here. We've got fractions on each side. We can just, this is a fraction too, we can just flip everything and we'll get lambda over C is equal to the square root of C minus U over C plus U. And then I'd have lambda naught over C, and we don't need the C's, we've got them on both sides. So we just get that lambda is equal to C minus U over C plus U times lambda naught. Now, when we studied the Doppler effect for sound, we had to be concerned with the speed of the source and the speed of the observer and distinguish between those two things. And we don't have to do that. We had different formulas depending on what was moving, and we don't have to worry about that with light because all motion is relative and the light travels at the same speed for observers in every reference frame. And so with sound, it was possible for, well, if you actually approach a moving source or a source of sound, the sound will be hitting you at a higher speed than if you were standing still. And that's not the case with light. It always just travels at C. So we have that going on there. Now, one thing that we might deal with is considering what happens if the speed u is slow compared to the speed of light. And maybe we could do some kind of a expand this in terms of the binomial theorem. And you might be thinking about that in the back of your mind. And I think that's one of the problems that I've got a little bit later on. There's also a transverse Doppler effect. And this is something, if a light source is moving with respect to you and part of its velocity is transverse, then there's a Doppler effect that happens in that case as well. And let's see. It ends up looking like this. It's F naught divided by gamma times 1 plus u cosine theta divided by c. And the theta is the angle between the velocity of the thing giving off the light and the direction that light is traveling at emission. So if you have an observer here, and out here you've got a source, and maybe the source has a velocity in this direction at some given time. Well, if the source is going to give off light that goes toward the observer, here's the direction the light's going to be traveling. And I'll put C with an arrow on it there. And then this would be the angle theta. Now, if all you have is transverse motion, like if it's only moving sideways and doesn't have any motion toward you, then that cosine theta is going to be the cosine of 90 degrees, which is 0. And for purely transverse motion, you end up with the frequency just equaling F naught divided by gamma. And it's a purely time dilation thing that's going on. It's because that source is moving with respect to the observer that moving clock runs slow. And so you divide by gamma to figure out what's going on there. So anyway, let's see what we can do with some of these things. Spectroscopic measurements of light at lambda equals 397 nanometers coming from a galaxy in Ursa Major reveal a redshift of 20 nanometers. Okay, a few terms. Redshift. That's shifted to longer wavelengths. And I think that's the only one we're going to run into in these example problems. And it's a problem. But as long as you remember it's shifted to longer wavelengths, it's okay. Blue shift is something shifted to shorter wavelengths. And it was, I think, called that in the early days because if you started from the middle of the visible spectrum, about 550 nanometers, which is kind of green light, if something is moving away, the light would be shifted to longer wavelengths. And from the middle of the visible spectrum, that's toward the red end of the spectrum. Similarly, if something was moving toward you, if the light was shifted to shorter wavelengths and from the middle of the visible spectrum, that was toward the blue end of the spectrum. The problem is in astronomy, people will often be studying things that are outside the visible spectrum, but they still use redshift to describe something that's shifted to longer wavelengths. Like you can, if you're studying infrared light, like the James Webb Space Telescope is, okay, it may be studying light from something that is moving away from us And so the light will be shifted to longer wavelengths, but they're calling it red shifted, even though it's moving away from the red end of the visible spectrum. So that's a problem. But that's what redshift means, is shifted to longer wavelengths. And if it's shifted to longer wavelengths, if we go back to our wavelength expression here, the only way it could be shifted to longer wavelengths is if you swap the signs here, because you've got a source that's moving away from you. These things are defined for a source approaching the observer, which shortens the wavelength, makes them blue shifted. But for this problem, we've got red shift. So we have to change the sign on the thing, on the U. So we'll have C plus U over C minus U is what we have to do. And then we've got lambda naught here. Well, this light at 397 nanometers, that's in the visible or in the laboratory reference frame that happens to be measured. In fact, this would be lambda naught is equal to 397 nanometers. Well, a redshift of 20 nanometers means the observed wavelength is 20 nanometers longer than this. And so lambda is equal to 417 nanometers, and lambda naught is the 397 nanometers. Okay. Well, I can just divide lambda by lambda naught over here, and I'll have 417 nanometers divided by 397 nanometers is going to equal the square root of C plus U over C minus U. If I square both sides of this thing, the nanometers will divide out. And I get 1.10 on the left side when I square both sides, and that'll equal C plus U over C minus U. Well, all I have to do is solve this thing for U, and I'll get it in terms of C. So kick that thing across, and I'll have 1.10 C minus 1.10 U is equal to C plus U. Let's see, subtract the C from both sides and add this to both sides, and I'll get 1.10 C minus C is going to equal 1.10 U plus U. And this will be 2.10 U. This will be 0.10 C. And it looks like U is going to equal 0.10 over 2.10 times the speed of light, which is about 0.0. I can keep two sig figs, so 0.48 times the speed of light, which if you actually multiply it out, it'd be about 1.4 times 10 to the 7th meters per second. So that's how fast it happens to be moving away. A distant galaxy. Well, hope that was fairly straightforward. The tricky part was having to recognize that you had to swap the signs. And I don't know. Let me look on this. Yeah, I've got it here. The Doppler effect for electromagnetic waves. For a source approaching, I've got the formula, and I say receding source, switch the signs. And receding means it's moving away from you. So that's kind of taken care of there. Let's see, a distant galaxy is moving away from us at a speed of 2 times 10 to the 7th meters per second. So that would be the U value. and I'd have to swap the signs on here. So I'd get lambda is going to equal the square root of C. Actually, those are the swapped signs, I think. So it's approaching. Yeah, those are the swapped signs. I was looking at the one for frequency, and for wavelength, those are the swapped signs. So we'll be using C plus U over C minus U times lambda naught there. But I want the fractional redshift, which is, I guess we can call this lambda prime. So lambda prime minus lambda naught. Lambda prime is the square root of C plus U over C minus U times lambda naught. And then I've got minus lambda naught. This would be the difference in the wavelengths. If I divide that by lambda naught, I get the fractional difference in the wavelengths. And what this ends up being is the square root of C plus U over C minus U minus 1 is the fractional shift in the wavelength. So, I guess I'll have to just plug in the numbers on this thing. So 2 times 10 to the 7th meters per second. Yeah, that'll work. Whoops, I've got these in the wrong order on top. C is 3.00. We've only got, well, this one we've got lots of sig figs on. 10 to the 8th meters per second. I'm going to get 3.2 times 10 to the 8th meters per second on top. But on the bottom, I have to do it in the right order because otherwise I'd have an imaginary number for this thing, which I don't want. And then I subtract 1 at the tail end. All right. 3.00 times 10 to the 8th meters per second minus 2 times 10 to the 7th meters per second. And this is going to give me 3.2 times 10 to the 8th on top. And this is going to give me 2.8 times 10 to the 8th on the bottom. So this thing I'm after is going to be the square root of 3.2 times 10 to the 8th. The 10 to the 8ths are going to drop out. And on the bottom, 2.8 times 10 to the 8th. Check that if you want. Minus 1. So and I get a difference of about 0.069. I can keep 2 significant figures on that result, I think, because that one is exact, actually. So that's the fractional redshift in this case. Okay, not huge, but a little bit. And that's just a number you don't really have much feel for in this case. But it's, I don't know, about 7%, I guess, is something like that anyway. Okay. Okay, earlier, I think we had one, or did we? Oh, that was maybe yesterday. We had a galaxy moving away from us at 0.87C, although I don't recall for sure anymore. But for this galaxy, what would be the observed wavelengths for the spectral lines in hydrogen that have wavelengths of 410 nanometers and 656 nanometers? I didn't get to show you demonstrations of the hydrogen spectral lines, or at least I don't recall. Maybe I did. But the 656 nanometers is the bright red spectral line that's in hydrogen. And then there's a kind of a teal or turquoise colored, yeah, it'd be more turquoise spectral line that's in 500 and some odd nanometers in hydrogen. And then there's a violet line that's at about 410 nanometers. So we're supposed to figure out the observed wavelengths for these things, but I'm going to try to minimize the amount of work that we actually have to do. It's moving away from us at that speed, so the wavelengths will be shifted to longer wavelengths. And here's what I do when I'm looking at these formulas. We've got lambda is equal to a C and a U and a C and a U. And if it's moving toward us, you have a minus sign and a plus sign. And that minus sign in the numerator will give you a shorter wavelength. But when it's moving away, you have it's shifted toward longer wavelengths. So you have a plus sign on top and a minus sign on the bottom. But I'm going to figure this out first because then I can just plug in those things, the 410 and the 656. Those are both lambda naught. So for this problem, the square root or the square root will be C plus 0.87 C. And on the bottom, we'll have C minus 0.87 C. And you may notice a C in every term here. Well, we'd have 1.87 on top and 0.13 on the bottom, and the C's divide out. So this ends up being the square root of 1.87 over 0.13. And I'm not going to try that in my head. Okay, so I get about 3 point. Yeah, only two sig figs really. Well, I had 3 on top, but only 2 on the bottom. So 3.8 is what this looks like. Okay, so it's going to be a wavelength 3.8 times as long. So for the 656 nanometer, the observed wavelength is going to be 3.8 times 656 nanometers. And I get about 2,500 nanometers. Okay, that's well into the infrared. About the upper limit of visible light is 700 nanometers. And so this is well into the infrared. And then that 410 nanometers, the wavelength that we'd see from that thing, 3.8 times 410 nanometers. We did parentheses there. I get about 1,600 nanometers. And this is well into the infrared as well. This is something like what happened when they discovered quasars. I was mentioning these yesterday, that for the light from quasars, they'd have spectral lines that were in visible light in a laboratory reference frame, but the light from the quasars was red shifted so far that it was well outside of the visible spectrum, and so they weren't seeing any spectral lines that they recognized, because some of them will have particular relative spacing between them, but when it's in a completely different part of the spectrum, and maybe you're not even studying infrared light from these things, it can be difficult to try and figure out what's going on. Okay, I think Yeah, these are maybe extra practice problems you could do. And you might, whoops. I must have printed this off in something that I think this is supposed to be delta lambda over lambda. Oh no, it'd be delta F over F naught. Would be plus or minus V over C. So if V is much less than C, you're going to be able to do some kind of a series expansion on this thing. So you might experiment with that a little bit. See, I might split it into two separate fractions and see what comes out of that. And maybe do two series expansions, one on the top and one on the bottom. But okay, you can try that. Anyway, that's it for this week. I'm going to post a homework assignment sometime between now and 2 o'clock, and it'll be due next Wednesday. It'll be on the first half of relativity, but I'm also going to post a homework assignment on the second half of the relativity, which we're doing next week. And that assignment will be optional for people who have missed an assignment or got a really lousy grade on some assignment, one of the homeworks or something like that. However, you should try those problems even if you're not going to turn it in, because it's on the part of special relativity we'll be studying next week, which has to do with relativistic momentum and relativistic energy. And there are questions on the homework about, or on the final test about that. So you'd want to try those out even if you're not going to write up a solution and turn it in. So we'll stop there today in the recording. Didn't see any